So if we look at, say, strong interaction, or what you call color interaction. So here you have the RGB, the color force. So you have RGB, that will be A, B, C, D, E, F, G, H, I. There are 9. Later you will see that there will be 9 fields, but of course only 8 are independent, for the final one is determined by the other. So there will be H gauge boson. Yeah. Eight color fields. So this is RGB. Okay. So here the gauge transformation will be I alpha dot T, where T is a 3x3 traceless matrix. So this T is 3x3 traceless matrices. Also called the generator of SU3. Generators, but they are banyak. For example, 3, if you campur the diagonal, it becomes 0. So 1 and minus 1 plus 0. So that will be 3 by 3, which is 9, minus 1 gauge boson. Which is called, and this gauge boson actually is the gluon. These are called the 8 bicolored gluon. You can imagine all this mixture. Actually, the last is the last gluon. If we still insist there are 9, it is colorless, so it cannot be colored. And also, if you tabulate all the possible matrices, you will see that there are only 8 possible. Let us concept of abelian force. So here, abelian versus non-abelian gauge theory. Or gauge forces. In general, this can be checked. In electromagnetism, again, I'm talking this about structure, not going into detail. In electromagnetism, remember that the phase, the E, I, alpha, say X, the phase, and this alpha could be the generator, so this alpha X is the generator. In general, the generator commute for EM. For the strong or color force, you have E I alpha dot t. I just write it here now. So this t, which is a 3 by 3 matrix, does not commute. It's a generator as well, but does not commute. I mean, actually, if you have all the T1, T2, 3 up to 3, 8, T8, sorry, you will see that if you multiply to the right or to the left, they don't commute. So you will see this idea of commute and does not commute. So the commuting one is called the abelian. The non-commuting one is non-abelian. We will show you here what does this mean by looking at how they travel, the boson. For example, electron here. This electron and this is another electron are interacting. Actually, this electron is traveling. This electron is traveling in this direction, and as it travels, it can emit. I mean, this is well known. Ramsalo, you will emit this photon. Okay? So say this is photon 1, this is photon 2. So it doesn't matter in this diagram as well that as this electron travel, you can emit this photon 2 first and then photon 1. The probability is the same. Dia tak kisah photon mana. And so Dirac equation describe this electron, and the group that are involved, this in EM is the U1. So this is U1 symmetry or EM. Yeah? These are EM interaction, and the generator yang diwakili tadi oleh Dirac matrix has no charge. So it doesn't matter whether you emit gamma 1, gamma 2, or gamma 2, gamma 1. Now, so this is EM. So EM is, well, for strong, suppose you have this quark of a certain color. Quark ni carry color charge. Let me write it. Color charge. So as it travel, it can emit. Katakan the color yang dibawa ni red, maka dia akan emit a red here. But since a gluon, so yang dia boleh emit adalah gluon. So that is the what you call it? That is the boson yang di so you need to have so the gluon is a color anti-color pair. Again, since we have not gone into detail of strong force, let me write it, gluon are color pair, or rather gluon carry color anti-color pair. So yang dia emit tu gluon lah, and then gluon G terus. Okay. Kalau nak dikirakan G bertemu dengan anti-G, so nothing happen actually. And then dia boleh emit gluon yang kedua. So this is gluon 1. This gluon 2, you have so this is gluon number 2, and here you have blue, okay, and so on. So the gluon carry color. So here definitely not equal to, kalau kau buat di sini macam ni, GB dulu, not possible. Kau ada rate apa ni, kuat to start with, suddenly kau nak emit yang ini dulu kan, GB, tak mungkin, not possible. Yeah. Sorry, anti blue. Sini boleh, tak sini ni yang masalah. Tak boleh. Kalau red, dia produce red, yang kemudiannya, so it's not possible here. So that's why here it's abelian. So the SU3 is a non-abelian. Why? Because the quark itself the gluon carry the force. Is charge, color charge. The gluon itself is charge. Dalam case photon dia tak carry charge. Jadi elektron tu dia biasa dia bercharge biasa. Dia tak bagi charge tu pada photon. Jadi sedangkan dalam kes ini dia bercharge dan dia mengeluarkan charge, transfer charge kepada gluon. So that's why it's non-abelian. So in the real world, the behavior of QED and the QCD is very different. Okay. If you have so for example in QED you will see an electron like this and a positron like this. It's schematic. Yeah? You have E plus, actually it could be E minus, doesn't matter. And here E minus, moving here. This is the photon field. For QCD, suppose you have a red quark, so the interaction here will be this is a green, red, green. When it emit a quark, so this will become a red, anti-green. Actually apa yang berlaku di sini kalau dipikirkan, I mean I shouldn't split this. Kalau kita tengok this, kalau kita tengok this red color just go down here and then continue di sini. Okay, you'll see that. Green dia naik dan belok ke kanan di sini. Tetapi bila kita draw, sebab kita kata yang atas ni yang emit duluan dan diambil oleh kuat yang di bawah. Kalau jadi maknanya red ni turun sebab dia ada yang emit, dan green naik atas tapi arah ke bawah, maknanya anti green. Itulah cara fine line diagram. Kalau kita bergerak pada arah yang berlawanan, kita jadi anti particle, ataupun kalau green jadi anti green. Kalau saya ubah, kalau saya kata yang bawah ni yang emit the blue on, saya akan tukarkan ni kepada anti red, dan arah dua-dua ni akan naik. Okey, akan naik ke sini. Ni adalah anti red dan yang ni jadi green. Green pula yang positif. Okey. Dan yang negatifnya ialah yang red yang turun. Tapi sebab yang ini naik, maka dia jadi anti red. Jadi dua-dua boleh. Ya. So it depend on where you want to nak kata yang mana satu emit the blue one. So it can be like that. And it can be you can get slightly more complicated in the sense that you can have a red in between, and then you have a green and a blue, for example. So where does this meet? You have a meeting point here. Blue, red. So here you have red and blue. Here you have blue and green. And here you have red and green. So you can have a triangular interaction here. Why is this more possible? Because gluon, they have strong interaction with itself. So more complicated diagram are possible. Why? Because gluon is very strongly interacting. Sedangkan photon, dia tak strongly interacting. Jarang kita tengok photon interact with itself. So the so-called photon ni, lepas tu keluar gambar photonnya ni, the so-called penguin diagram ni jarang. Tapi bagi gluon, it is more likely. And actually that is the reason why there are no free quarks, because all are strongly bound by gluon. So so as a comparison, if you have a E plus E minus interaction, for example, you can have, say, photon, one or two photon interacting between E plus and E minus. Whereas if you have a similar comparison between quark and anti-quark, say, not only you have a field of gluon here, but gluon themselves start interacting with itself. Very complicated. So the gluon interacting with itself. So, in terms of field lines, so these two, when transformed into field lines, you will see that katakan electron and positron, they have a field lines that come like this. These are field lines. This goes out. Those are field lines. Yang ni tunjukkan bosonnya. Whereas for quark and anti-quark, you will have a very small tube. Because they are strongly interacting. They are not open. So this behavior of quark make them very different from make the QCD very different from QED. For example, the distance of interaction with quark is very, very small, whereas for photon EM interaction, Tuhan ciptakan kita boleh berkomunikasi. Pakai handphone apa semua ni elektromagnetik. Quark tak boleh. Kalau kamu nak berinteraksi menggunakan gluon, kamu sendiri kena jadi Mr. Quark. Mr. Quark ni sebetulnya wujud dalam cerita Alice in Wonderland. Jadi perkataan quark tu diambil daripada cerita Alice in Wonderland. So what happened was, if you try to pull a meson, meson ni mengandungi dua quark and anti-quark pair. So if you have a quark, anti-quark here, this one should be a curly. Okay. So what holds the quark and anti-quark is gluon. So you try to separate the quark and anti-quark. How do you separate? So quark and anti-quark is a meson. So how do you separate quark and anti-quark meson? By collision. Bila you collidekan meson ni, it will what you call it, scale change. What you call it, behavior at short distance.